Welcome to my presentation. Today I'm going to talk about simulation of hybrid Rio connectors. This is a joint work with Alireza Farhadi and Farhad Arbab. I'm a senior postdoctoral researcher at the School of Computer Science of the Institute for Research in Fundamental Sciences, IPM. I received my PhD in computer science from University of Warwick. I'm interested in applying formal methods to software aspects of cyber-physical systems. Here is the plan of my talk. First, I will give the introduction and objectives of this work. Then I will introduce you to Rio coordination languages for component-based systems. Then I will give a specification of hybrid systems in Rio. Then I will give a transformation of hybrid Rio specifications to SMC models. A case study based on a strategy-based control systems will be followed. And finally, conclusion and future works. Cyber-physical systems consist of a large number of interactive dynamic components such as sensors, actuators, controllers, and etc. This leads to the coordination problem. In this work, we are trying to address the coordination problem. Of course, there are other challenges in design, simulation, and verification and security of cyber-physical systems. In the case of verification, we have methods of correctness by constructions, such as the formalism, which in this work will be presented, versus model checking, theorem proving, abstraction interpretations, and etc., which they need to address large state space. So I'm looking for suitable formalisms that to some extent address these concerns. It should specify coordinations, it should be compositional and have formal semantics, it should be high level, and it should ensure correctness. So these are concerns which I need to address. And Rio, to some extent, address some of these concerns. It is interaction-centric, it is exogenous, that means that it doesn't care about the internal behavior components, it's focused on interactions, the way they interact with each other, and more importantly, it is compositional. So the objectives in this work is to model component-based and compositional hybrid connectors in high-level coordination in real language, defining composable new primitives for designing well-defined coordination layer in component-based cyber-physical system software, and then using the statistical model checking approach to check properties of hybrid real connectors through numerical simulation of their behavior and the physical environment. So first I will give an introduction to the Rio coordination language. There are two basic types of primitives. Node types with respect to the flow of data consist of source, sink, and mixed. And the other primitive is called channel, which is basically the relation and constants on the flow of data, like synchronization, lossy sync, drain, or filter. These are the graphical representation of the channels. So in sync AB, it's a channel which cyclically gets a data item through its end A and synchronously, atomically outputs that data item through its ends B. So this is about the relation of the data, relation on the flow of data from the port A to B. In Rio, the goal is to compose these simple relations to get more complex relations, to get more complex connectors, and to specify more complex interaction in the component-based systems. So, in transformation, for example, as another example, it behaves like a sync channel, except that it applies the unary function f to every data item that is received from A. The channel loses all data items taken from A that are not in the domain of the function f. Now, of course, I have other channels here, which you can look into their formal definition. For the case of hybrid systems, I introduced a new primitive called hybrid timer. So in the hybrid timer, we have differential equation as well as a resetting condition in the specification. So it is a specific variant of the transformer channel that expresses hybrid behavior by differential equation represented by ODE, ordinary differential equation. And also for this, for taking the initial value, I need to use a 5-foot channel of real to take initial value. So in the implementation, I need a 5-foot channel. Also, the parameter Q specifies a condition that when it's satisfied, the differential process will be reset. So it's a resetting condition. So consider a model of a thermostat that coordinates a user and a heater components. The running of this simple model leads the heater to start and stop depending on the temperature, which varies according to EDE. This is an example of a hybrid relay connector. To express this model in hybrid relay, we construct a connector out of ordinary relay channels and 2 hybrid timer channels, one for the heating up and another for the cooling down, the room temperature. So here is the example of a hybrid connector in the hybrid real specification language. I have 4 ports set feedback start and stop between the user and the heater and the connector. I have ordinary real connectors like filter and replicator sink, and I have 2 hybrid timers for heating up and for cooling down, with respective resetting conditions and the involved ports. And these compose together to get the whole example of thermostat. Now, note that here we don't care about the internal mechanism of user or heater itself, which is focused on the way they interact with each other, and also the physical environment. As for formal semantics of hybrid relay, it is based on a hybrid variable constraint automata where the transitions are labeled with data constraints, port names, and reset conditions. And the more complex behavior of the connectors can be described by defining specific multiplication of these automata. So, as for a simple example, the expiring 5-foot channel where a data item will be lost if it is not taken out from the buffer through the sink and within tau times of units after it enters the source node. This is the hybrid constraint automata corresponding to this 5-foot channel. So the transitions are labeled by the involved ports, constraints on the data, and also resetting conditions. And the states also, they have ordinary differential equations in their specification. For more information and formal definition, please refer to this paper and also other papers in the references for the classical constraint automata, classical real semantics. What is UPAL? UPAL is an integrated tool environment for modeling, validation, and verification of real-time systems modeled as a network of time automata. By modifying this classical model checking framework, where the non-deterministic choices are replaced by probabilistic choices, we get a new model where their behavior defined by stochastic time automata, and the interactive systems components are modeled by a network of synchronizing stochastic time automatas. And it has a tool support for verification of these probabilistic properties and simulation and validation. Transforming hybrid real is our goal in this work in order to get advantage of the UPAL tool support. To this end, for each type of view channels, we define a template where ports are parameters, and for the instantiation of these things, instantiation of these templates, we need to incorporate broadcast channels corresponding to the connector ports. So for each port or each interaction, we need to define one or more broadcast channel which propagates this interaction through the network of UPAL automata. Here is an example. So in the case of sync channel, where I have two input and output port, here I have two broadcast channel. I have readiness variables for defining readiness predicates, which ensures how to take and dispense data. I have locations. Some of them are called committed locations, and these locations are those who can synchronize with other locations in the network. So once I get data item through the ends, the input port of sync channel, so I can get the input from the broadcast channel in. I can update the readiness variable to false to ensure that no other item will come through. And if the output port is ready, then I can send it through the channel out, and then I can update the readiness predicate. So by this way, we can also define other templates for the UPAL, for the hybrid real connectors. In particular, for the timer here, we have differential equations in the definition here as a logical predicates. And I can define this. Okay, so we define the transformation rules as follows. So we have two kinds of constraints: synchronization constraints and data constraints. In the synchronization constraints, we have the involved ports, and the data constraints, we have the logical predicates that enforce the constraints of the flow of data. In case of hybrid timers, we have the differential equations in the data constraints and the conditions for resetting conditions for the outputting. By applying this rule to the example of the thermostat, we get this network of UPAL automata instantiated at the port as broadcast channels, and of course we have the logical predicates ensuring the data constraints in each template. So in our example, the user could select from three ranges of temperatures. Here, as soon as the feedback is received by the user, it selects the next range, and it will process. This process will be repeated indefinitely. And we have a high and low threshold here, and the clock X is a trajectory in the hybrid timer, and in this example, the temperature. So as long as we get the feedback, we have this kind of dynamic, and we can actually, through the UPAL, we can visualize this trajectory, which gives some sort of validation method as well. So this is the way our example works. This is the result of running an example in the UPAL 2. Well, how is the model composition is done? Of course, model composition in UPAL is done by a sequence of synchronization that's flattening. In a network of automata, multiple UPAL channels carry out single channel actions. This is in contrast with real, where multi-actions are allowed. We examine the relation of our transformation of the hybrid constant automata semantics of a hybrid real connector, which provides a way of proving correctness. So in here, what we do is that we for each multi-actions in the transition graph of hybrid constant automata, we have a sequence of single actions. Here we should define a location vector and discrete and continuous evaluation of the variables to get this transition graph corresponding to the impal automatas. And then we simulate each multi-action with a sequence of single actions. The strategy-based control is where we have building of several rooms and movable heaters and local thermostat and central control and control strategy which can take into account non-functional properties, for example, energy efficiency and etc. So in this example, each room temperature is monitored by a local thermostat. A central control can move a heater around the rooms and turn it on and off according to the control strategy. Specifically here we have two adjacent rooms and a heater which can move from one room to another according to the control strategy. So here's how we model the behavior of this case study. For the simplicity, we focus on synchronization constraints. So essentially, we need a mover. We have to send a request and get the heater and release in the case when we don't need it anymore. So we model this into the hybrid connectors. So we have three kinds of connectors here: two regarding the rooms and the heaters, one for the adjacency relations here. So this is a graphical representation. Of course, in the implementation, we have a textual representation, which is perhaps easier to follow. But just to show that how the interaction goes, we put in the graphical representation in the picture. One good thing about this is that we're using subconnectors. We can see the reusing subconnector here. We can add simply another room with this pre-specified components here. So I can use another room, other adjacency relations, another heater. So I can have two heaters moving into the three rooms. As for implementation, we extended the classical real connectors compiler for the textual real, and then we implemented the transformation into it by defining the implement templates. So the result of the applying to our case study, applying the transformation to the case study is represented here. You can see that the heater actually moves around the rooms and it changes temperature accordingly. So this is it shows that in the time close to the point 29, it moves back to room to point 58. So you can see the trajectory, which is sort of validate the model. And for the probabilistic properties to be verified with this impal SMC tool, we model the chance of heater movement between the rooms. So we get that both properties, that whether it is present in room 1 and room 2, both properties are satisfied with high probability, which shows that actually it moves around these two rooms. So we can have even more complex probabilistic properties, but it can be easily specified by the impal SMC and statistical model checking tool, and it can be verified efficiently. So in this work, framework for high-level reusable composable specification of coordination mechanism in cyber-physical systems is introduced using real language. A transformation is given for a hybrid real specification which produces impal SMC network of hybrid automata. Using the tool support of impal, we do simulation, validation, and verification of these case studies. As for future work, the main future work is implementing a composition operator, for example, a product of hybrid constant automata, and apply various compilation optimization that are specific to the real semantics. Currently, composition, as I described before, is done by UPAL on a flattened model of network hybrid automata, which of course it introduces overhead for a more complex and larger example. Comparing with actor and event-based modeling approaches for CPS, like Beep or Rebecca, is another line of work, especially to understand why interaction-based model can be more effective in what cases it could be more effective. For additional detail on definition of the real semantics, hyperreal semantics, and other properties of these models and verification schemes, please have a look to the following references. Okay, so this is the end of my talk. Thank you very much for your attention.